Hi, welcome back to Moose Chemistry. This is electron configuration of iodine. I. No, it's I. Anyway, it's element number 53 on the periodic table. Okay, so write down a 53 here. And its atomic mass number, which is the AMU, is 127. Okay. So since the atomic number is 53, that's the number of protons. Pretty darn easy, huh? And since it's electrically neutral, it's got to be 53 electrons also. What about the neutrons? That's right. Well, we go AMU minus protons equals the number of neutrons. So we go 127 minus 53. That's going to give me 74 neutrons. Pretty darn snarly is what I have to say. 74. Amazing, huh? Let's go ahead and get rid of some of this extra writing here because we don't need it. We've already done it, right? Okay. Now, hey guys, when we do the electron configuration, we have to think about this. The S subshell holds 2 electrons, the P subshell holds 6 electrons, the D subshell holds 10 electrons, and the F subshell will hold 14 electrons. We're using the off-ball principle, which basically says that we're going to fill the lower shells first, then the upper shells. And we're just doing the diagonal rule. Just follow the red arrows, and you should get there. Until you run out of electrons, of course. Watch. 1s2. Cool. 2s2. Amazing. 2p6. 3s2. 3p6, 4s2, 3d10, 4p6, and 5s2. 4d10 and 5p5. All right, we're almost there. Our orbital notation, guys, is Hund's rule. In Hund's rule, more or less, you're supposed to put an up arrow in every suborbit of that orbit until you start the down arrows. Okay, 1s. It's only got one suborbit. There you go. 2s. See that? 2px, 2py, 2pz. See how easy that is? That's Hund's rule right there. Nice. And then we just kind of repeat these patterns as we go across this orbital notation. Again, until we run out of electrons. Doesn't matter how many suborbits you have, Hund's rule works the same in all. Pretty darn look at that. Okay, we're getting close to the end. 5s up and down, and then of course it's 40x squared minus y squared, 40xy, 40yz, 40xz, 40z squared. Now we have 5 electrons left, right? 1, 2, 3, 4, and 5. All right. Well, iodine is right next to xenon, but you still can't use xenon because xenon's after iodide, so it's going to be krypton. Okay. And we're going to look at our valence shell, which is this guy right here. Pretty darn cool. And we're going to write in numerical order, of course. 4d10. 5s2, 5p5. That was easy. What about our quantum notation and Pauli exclusionary principle, which says no two set of quantum numbers can be for the same element, right? Or the same 2 elements or different elements or whatever. Actually, Pauli exclusionary principle basically states this, that no 2 elements can have the same set of quantum numbers. So I'll just kind of end that confusion there. It is in the P block. That's exactly right. So since it's the P block, it's in period 5, so the number for the n value, our principal quantum number, is going to be 5. Our angular momentum number is going to be 1. Our magnetic number goes 0, minus 1, 0, 1, right? Minus 1, 0. So it's going to be 0 because it's the 5th element over. And it's right about here on the P block, more or less. So it's going to be 0 there. And look at this last arrow, that one right there. It's going down. So it's going to be 1/2 negative. Well, guys, guess what? That's it. You be snarly, and we'll see you back here at Moosing Chemistry.